So we have a data set, dot tolerant and the conventional, that are the two factors, and there's a yield of dot tolerant genotype and yield of conventional genotype. So what we do here, so we want to check whether the dot tolerant genotype is normally distributed or not. So for normal distribution test, we use Shapiro-Wilk test. This is the formula for Shapiro test. So we just want to see the yield values in the treatment drought tolerant, first one. So I just need to change non into data. Data, data. For the drought tolerant, error in Shapiro. There's a 1 minute. There's error here. Data. One. Yeah. For the data treatment that is conventional, I don't know why we are not getting for the data treatment drought tolerant. So drought tolerant, drought tolerant. We should get something for this. Yeah, we got it. For the Shapiro's test for the drought tolerant, the p-value is greater than 0.05. That it means the p-value is greater than 0.05. It means the Shapiro-Wilk test, what it tells, if there is the 0.05, then there is a then the distribution is in probability curve. The distribution is a normal distribution. If it is less than 0.05, then it's not a normal distribution. So if you just check the conventional also, the p-value here is 0. It's greater than 0.05. This is 0.96. Then both to drought tolerant and conventional is under normal distribution. Why? The p-value is 0. Greater than 0.0. So we can also plot QQ plots for this. So we can have a QQ plot for this, and we can see how they do this. So we need to check data name. This is the data name. I have done another data set called non. So I'm just changing whatever the data name I have here. The data name is here itself with the data. So we just check the QQ names. See, this is the QQ plot. Here you can see the QQ plot. So this is the line is the theoretical distribution, and the circles is the real distribution. So more or less there is a strong association between theoretical and real values. Then it's a normal distribution. If the values is somewhat away from the theoretical distribution, then it's not normally distributed. So these values are now normally distributed. The same we do for the conventional. If you couldn't able to understand the data set, I can tell you the what really the data is there. So we have a two varieties called one is a drought tolerant variety, one is a conventional variety, and we have a yield of these two varieties, and we are just checking whether the distribution is normally distributed or not. So for the conventional, we check again. So again, this is also normally distributed. Why? The both are in a same association. The QQ plots, the theoretical values and the real values are in are aligning with same line, are aligning with narrow gap. So that's why it is normally distributed. So we can also check with plot densities. The so normal distribution curves. The code for this is we use plot density curves. So we are just subsetting the two data set into conventional and drought tolerant. So we got DT is a dot tolerant data, and CB is the conventional data. So when we go for the plot density for the dot tolerant, so we get the plot like this. It looks like more or less normal distribution. So when you go for the conventional yield, conventional variety, it took less. So this is exactly normal distribution. So whatever data we have is a normal distribution. So non-parametric test is used when our data is not normally distributed, but our data is normal distributed. Even though our data is normal distribution, for the demo, I'm going to do some test in the same data. I'm going to do some non-parametric test. Though it's a normally distributed, for showing you guys, I'm going to do some non-parametric test. So first is Wilcoxon test. This is the code in the r.wilcox.test. So where the yield is our dependent variable and treatment is our independent variable. So we get for Wilcox test data is equal to the capital D because R is case sensitive. So again the p-values less than 0.05. It shows there is a significant difference between drought tolerant and conventional. And if it is a normally the DOE data is normally distributed, where I'm just doing the non-parametric test to show a demo for you guys. And the second data set is for the critical values test. We'll go to the environment, import data set from Excel. Whatever the files I have shared you, just import them. This non-parametric test. There is a separate sheet called critical values test. It has a different fertilizer dose, A, B, C, and this is their crop field. We just save it as a cruise as the name of the data set. So when we use the critical value test, the name of the data is cruise. So critical values test we are using for the crop yield and the fertilizers. So there is a different doses of fertilizers, and each dose is having a separate crop yield. So we are just comparing in three groups whether there is a difference or not by using critical values non-parametric test. So again, the p-value is less than 0.05. So 2.399 to the 10 to the power of minus 6 is less than 0.05. Then it shows there is a significant difference. So we need to go for the post hoc test. The post hoc test is a pairwise Wilcox test. I told like in parametric in ANOVA, if you do the post hoc test, there is a Tukey test and Fisher's elastic test. But in non-parametric test, if you do go for the post hoc test, there is a Wilcox test. Whatever we did previously here, we did here Wilcox test here. Yeah, Wilcox test. So Wilcox test compare between two groups at a once to show whether there is a significant difference or not. Cruise. The data name is Cruise. We just need to change the data name to Cruise. Control and C. So between how to read this table is very important. Between A to B, the p values is here is the B and here is the E. The p value is less than 0.05. Then there is a difference between fertilizer dose A and fertilizer dose B. And BB is the same thing, so there is no comparison. Between C and A, the p value is less than 0.05. There is a significant difference between C dose and A dose. Between C and B dose, the p-value is less than 0.05, there is a significant difference between B dose and C dose. So if you want to calculate the Spearman correlation, there is a code for this. So we need to separate each fertilizer dose as a separate variable. So that's what we are doing here. Close. So we're just changing the name of the data set. So first here we are making three variables of fertilizer dose A, fertilizer dose B, and fertilizer dose C. So we got the three variables, and we are going to plot the scatter plot between Y1 and Y2. This fertilizer dose A and dose B. So this is the scatter plot. So you can see the scatter plot. There is no linear relationship. You cannot see any proper trend here. It's a mixed trend. That's why we need to calculate the Spearman correlation. If there is a proper trend of positive slope or negative slope, then we could have went for Pearson correlation. There is no proper trend here. That's why we go for Spearman correlation. So we just go for the test as a code as test. We just need to mention here as a Spearman. So just see the Spearman values and here. The Spearman correlation is minus 0.444. The p-value is less than 0. It's greater than 0.05. So there is no significant correlation between A fertilizer dose and B fertilizer dose. Why? The p-value is greater than 0.05. So again we come for the one-way ANOVA. So for ANOVA we are going to do with the same data which we used before in the first study. So we are going to import the data. The same data which we use for the yesterday data set. This is a wheat data. Can put ANO, the data name is. So the data is again is a different genotypes of the wheat varieties and planted in different countries, and this yield values. So what we are able to doing here, so we need to calculate the one-way ANOVA, single ANOVA between yield and genotype. So our data name is ANO. So for ANOVA, the R short name for the ANOVA is AOE, AOV. That's the ANOVA model, ANOVA code for the ANOVA model in R. Just click it here. So this is the ANOVA. We got the ANOVA here. That's the genotype degrees of freedom, residual degrees of freedom. That's the error. Sum of square, mean sum of square, F values, and the table F values. If the F value is greater than table F values, there is a significant difference. But the F value is less than table F value. That's the PRF values. There is no significant difference here. That's why if you do the post-hoc test, we get the P value greater than 0.05. See, if you see the P values, all the P values is greater than 0.05. So this is a one-way ANOVA. Two-way ANOVA, what we are doing here, we are taking the ANOVA model with yield plus genotype plus country. The data set is AOV. So we have a country information here. This data set, we have a genotype, country, and yield. So we are considering two variables. Genotype as a one variable, country is another variable. So when you do ANOVA for this, So you got the genotype, source of variation is genotype, source of variation is country. The both is significantly different because the calculated FL is greater than table FL here. So both are significantly different. So when you calculate between the genotype, what is the difference, significant or non-significant? Calculate Turkish HSD test. This is a post-hoc test. So this is the so between Bagula and Bacanora, there is no difference because the p-value is greater than 0.05. So there is no difference between genotypes, but there might be difference between countries. Yeah, so there are many countries which shows the value is less than 0.05. Suppose if we take this as 0.001. Between Bolivia and Argentina, the yields are significantly different. So there are different packages you can explore. Rather than doing ANOVA directly here, there's a package called Agricole. You can note down in your notebook. There's a package called Agricole. In Agricole, there's a separate manual is there. It's very easy manual. If you know simple codings, you can do this. There's a specific for all kind of ANOVA models, all kind of ANOVA post-hoc test. So everything is included in Agricole. Just have a look whenever you get time in Agricole and try to have a fun with RStudio. And you can also do the DMRT test. So in Agricole, if you just install the package Agricole, I have already installed the package Agricole in my. Uh, it's already available in my laptop. So I'm just opening the library Agricole. So I'm just doing the ANOVA model here. So sometimes many people ask how to do the Duncan multiple range test. So DMRT test. So many people they use in soil sense, seed technology and all those tests. So DMRT test is the same as the simple code for the DMRT is Duncan test. It's very easy code. Just select and click this here. So you get the DMRT test here. So you get for each there is a couch. There is no difference between genotypes. If there was a difference between genotype, it would have showed A, B, B, C, C, something like that. So everything is A. There is no difference between any genotypes. See, there is no difference between any genotype. This is DMRT test. So here you will come. Here it ends to the whatever the coding we learned for non-parametric test on ANOVA. And if you have any doubts regarding the theoretical thing what I have taught today, and any coding problems, please let me know.